Good morning. Today I'll be talking about the use of acrylate and titanium dioxide antennas through the process of stereolithography and the main focus of microstereolithography. The paper that I researched was the fabrication of three-dimensional microphotonic crystals of resin incorporating titanium dioxide particles on their terahertz wave properties. This was a paper out of Japan written by these three authors here. It was included in the American Ceramic Society, Volume 90 in 2007, and the main focus was to analyze the creation of crystals and how well they work to create photonic, or to work with their photonic band gap on the terahertz scale. And the main question is, can microstereolithography be used to fabricate these 3D photonic crystals on this micro scale and be able to work well? The material used was a KC 1184 acrylate resin, and it was incorporated into the titanium dioxide powders with the mean particle size of 200 nanometers, and it was mixed at 40% weight volume. The process conditions examined were they used microstereolithography compared to stereolithography to get down to a smaller scale, and then they looked at the diamond structure, microphotonic crystals, and the electromagnetic wave transmission. And what they used for these were a CAD microstereolithography system, which would be the same as a stereolithography system, but it came out in smaller layers. They did 400 layers on I think it was 200. No, it was 400 layers on 200 micron diamond part. And then to view these, they used digital optical microscopy and scanning electron microscopy or microscopy. So the first study was how well do these cure when exposed to the microstereolithography. The picture on the left shows using 10 micron layer thickness, and then the one on the right used 5 micron layer thickness. And as you can see in the 10, there are gaps in between the layers, so it did not cure together all the way, but in the 5 you don't see any gaps. And this was for cure depth, and it also showed similar properties when they looked at lateral resolution as well. And so even at 10, while the layers were fully polymerized, there was poor connection between the two, but the same polymerization occurred at the 5 microns, and we see good connection between the layers. And then the next main study was how well does the band gap line up with what theoretically should happen and what they measured. And so on the left, the picture is the measured band gap, which spans from 280 to 360 gigahertz, and this is on a terahertz scale. And then the one on the right is the calculated one, but they were only looking at this shaded portion here, which also was on the same range from 250 to 360 gigahertz. So they concluded that by using microstereolithography, they could achieve the same relative photonic band gap out of these crystals. And then from summary, the key conclusions, the fabrication shows the same dimensions and no deformation. This was they viewed a full-scale diamond crystal, and they saw no deformation when they measured between the trying to think of how they worded it. They measured from one point to a second point on it, and there was no deformation throughout the particles. And then the microstereolithography worked well when creating the fully 3D crystals, and it was successful in creating the same photonic band gap. And then, as this paper was written, in 2007, being nearly a decade old. Their main focus was try to create these in order to include them in imaging processes or communication or things in the medical field to get these frequencies when needed. And I thought this was a good kind of first look study at trying to achieve this scale in order to incorporate it in these things. And now that we're nearly a decade past the paper written, I feel that they've been incorporated, but I thought this was a good first study.